Hello, my name is Peter McCown. I'm the Vice Principal in charge of Public Engagement here at Queen Mary. This series, we're looking at some of the world's best mathematicians, and this particular video features Art Benjamin. So Art Benjamin is famous across the world, both in mathematical circles but also in magic circles, for his ability to do amazing, rapid mathematical calculations in his head. And tonight he's going to explain a little bit about how the maths behind those works, and gives a virtuoso performance in which he'll actually blow your mind. So have your calculators ready, because you will probably need them. I give you Art Benjamin.
Good evening, ladies and gentlemen. My name is Art Benjamin, and I am a mathemagician. What that means is I combine my loves of maths and magic to do something I call mathemagics. But before I get started, I've got a quick question for the audience. By any chance, did anyone happen to bring with them this evening a calculator? If you have a calculator with you, perhaps on your phone, and you're comfortable using it, raise your hand. I'll need a few people to help me out. Oh, some eager volunteers. Great. I'll save you for later. How about, did you want to help out? Okay, we got 1 and 2 and 3 and 4. Would the 4 of you join me up here with your calculators? Let's give these volunteers a nice round of applause. Come on down. Over on this side, please. Terrific. One more round of applause for our brave volunteers. Now, since I have not had the chance to work with these calculators, I need to make sure that they are all working properly. Would somebody get us started by giving us a 2-digit number, please? How about a 53, did you say? Okay. And another 2-digit number. How about you? 12. Multiply 12 times 53. Make sure you get 636 exactly, or the calculators are not working. Are all your calculators working? Give them a round of applause. Now, I notice that took some of you just a little bit of time to get your answer. That's okay. I'll give you a shortcut for multiplying even faster on the calculator. There's something called the square of a number, which most of you know is taking a number and multiplying it by itself. For instance, 5 squared would be 25. 6 squared would be 36. 73 squared would be something else, right? So
1,329.
That's correct. Okay. Now you used a shortcut on your calculator. Do that. So what I'm going to try and do now is to square in my head 5 2-digit numbers faster than they can do on their calculators, even using the shortcut methods if you have one. So what I'll ask is 5 people here in the first row. How about 1, 2, 3, 4, 5? Each yell out a 2-digit number, and if you would square the first, the second, the third, the fourth, and the 5th one, I will try and race you to the answer. So quickly, a 2-digit number, please. 75. Okay, next. 86. Next. 65. Next. 78. One more. 42. Would you call out your answers, please?
Correct. 5,625.
5625.
7,396.
7396.
4,225.
4225.
6,084.
6084. And finally,
1,764.
give them a round of applause. Let me try to take this one step further. I'm going to try to square some 3-digit numbers this time. I won't even write these down. I'll just call them out as they're called out to me. Anyone at all call out a 3-digit number. Anyone on our panel verify the answer. A 3-digit number, anyone?
356.
What was that? 356 is 126,736.
Correct.
Correct. Good. Give me a thumbs up if it's right. Let me know if it's wrong. I'll make. How about another 3-digit number? Go ahead. 345 is 119,025. 119025. Great. Another 3-digit number. Go ahead. 3 digits. 417 is 173,889. 173889. Good. One more 3-digit number, sir. 987 is 974,169.
Yeah.
Thank you. You're fast. All right, let me try to take this one step further. Going to try to square a 4-digit number this time. Now, I'm not going to beat you to the answer on this one. Definitely not you. But I will try to get the answer right. To make this a little bit more random, let's take 4 people. How about in the second row here? 1, 2, 3, 4. Call out a single digit between 0 and 9. That will be the 4-digit number that I'll square. 7, 7, 2, 1. 7, 7, 2, 1. This will take me a little bit of time, so bear with me. 50, ooh, this is close. Oh, very, very close. All right, all right. 7721 was the number, right? Okay. How about 60 million? So far, so good. Or is it 59 million? 59 million. Okay. All right. Let me try that one more time. 59 million. Now someone's ticking there. 613,541? 841.
Yes.
Thank you very much. That took harder. That was longer than it should have. I'll tell you what. I would attempt to square a 5-digit number, and I can, but unfortunately, most calculators cannot. Although, yeah, I think yours can. I'll talk to you later. In the meanwhile, let me conclude the first part of my show by trying something a little trickier. Let's take the last number on the board here, 1,764. Would you each enter 1764 on your calculator? And instead of squaring it this time, I'd like you to take that number and multiply it by any 3-digit number that you'd like. But don't tell me what you're multiplying by. Just multiply it by any random 3-digit number. So you should have as an answer either a 6-digit or possibly a 7-digit number. How many digits are in your answer? 6. You have 6? 6. 6. 7.
6.
6. Is there any possible way that I could know what 6 or 7-digit numbers they have? Say no. Good. Then I shall attempt the impossible, or at least the improbable. What I'd like each of you to do is to call out for me any 5 of your 6 digits, or in your case, 6 of your 7 digits, in any order you'd like. 1 digit at a time, I shall try and determine the digit you've left out. So starting with your 6-digit number, call out any 5 of them, please.
Any order.
Any order.
6, 7, 4, 2, 4.
Did you leave out the number 1?
No.
You've got a 6-digit number?
Yes.
Call out 5 of those 6 one more time. Call out the same 5 if you can.
2, 4, 4, 7, 4.
Did you leave out the number 6?
Yes.
Okay, good. That's 1. You've got a 6-digit number. Call out 5 of your 6 loud and clear.
91965.
Did you leave out the number 6?
Yes, I did.
Same as him. All right, that's 2. You've got a 6-digit number. Call out any 5 of yours in any order.
24669.
24669. This one's a little tricky. Let me get back to you on this. Don't forget it. You've got a 7-digit number. Call out 6 of yours in any order.
011728.
I think you left out the number 8.
Yep.
Great. One more. If you've got a 6-digit number,
Yep.
call out any 5 of them. Really scramble them up this time.
Okay. 85851.
Interesting. You know, I'm having some trouble with yours too. I'll tell you what, both of you, do me a favor. Concentrate on the digit you left out.
Magic.
Doesn't do any good. It just looks dramatic. And yet, I seem to be getting a lot of nothing. Which of you left out a 0? No wonder I was getting a lot of nothing, but not from you. You just normally think of nothing. Is that it? Okay. Concentrate on your number this time. I think you left out the number 9. Fantastic. And let's give all 5 of these people a nice round of applause. Thank you very much. Thank you. For my next number, I'd like to present something we mathematicians refer to as magic squares. Now, how many of you out there do Sudoku? Magic squares are kind of like Sudoku on steroids. Now, I've done such an extensive study on magic squares that I'd like to create one for all of you right before your very eyes. But for this, I'll need another assistant, someone I do not know, and I do not know you. What's your name?
Sarah.
Sarah. Let's give Sarah a nice round of applause. Come here, Sarah. Sarah, if you would stand there. Is that S-A-R-A? Sarah, let me ask you another question, and if it's too personal, I can change the question. Sarah, are you willing to share with us your birthday, including the year?
Yes.
Great. Sarah, what is your birthday?
The 18th of September.
18th of September.
1991.
1991. Oh, lots of nines in there. I love nines. Okay, Sarah, if we were to add the numbers in your birthday together, let's see, 18 plus 9 is 27, plus 9 is 36, plus 1 is 37. So 37 becomes your magic number. What I'm going to try and do now, Sarah, is to fill out this box in such a way as to get your magic number appearing here as much as I possibly can. This will take me a couple of seconds, so bear with me. I think that works. Sarah, would you choose for us any row? Row number 2, 3, or 4? Which would you like? 3. All right, class, together. 2 plus 10 is 12, plus 8 is 20, plus 17 is 37. The others were 18, 27, 36, 37, 8, 10, 27, 37, 9, 25, 28, 37. Would you choose a column, Sarah? 1, 2, 3, or 4? 3. All right, class, 9 plus 17 is 26, plus 8 is 34, plus 3 is 37. The others were 18, 26, 28, 37, 9, 11, 21, 37, 1, 11, 28, 37. How about that? Now, Sarah, I'm not through with you. I decided that since this was your magic square, based on your birthday, at no extra charge, I would give you these diagonals as well. Check it out here. 9 plus 10 is 19, plus 17 is 36, plus 1 is 37, 18, 20, 28, 37. But I didn't stop there either. I decided since this was for Sarah, wouldn't it be great if we could get these 4 in the center to add up as well? Check it out here. 2 plus 17 is 19, plus 8 is 27, plus 10 is 37 to add up. And I figured, heck, as long as we got that group of 4, let's have a party. We may as well get this group of 4. 18, 27, 29, 37, 9, 10, 20, 37, 2, 12, 28, 37, 8, 25, 34, 37. But did I stop there? Did I stop there? No, sorry, you may have noticed I got this group of 4, 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 this group of 4. Now I have to apologize, Sarah, I was not able to get this group of 4 nor that group of 4 to add up, but I had to do it that way if I was going to get these 4 in the corners. I knew that would be important to you. 18, 19, 28, 37. But wait, here's the cool part. Sarah, not only do those 4 numbers in the corners add to 37, if you look at them closely, you'll see we have 18, 9, 91. I was able to give you your birthday a second time. I thought you'd like that. So please keep this as a souvenir from me. And let's give Sarah a nice round of applause. Thank you, Sarah. Hey, speaking of birthdays, by any chance, does anyone here happen to know the day of the week that they were born on? If you think you know your actual birthday and you're willing to share it, raise your hand. All right, starting with you, sir. What year, first of all? Either one. 1993. And what month? November what? 10. Was that a Wednesday? Yes, good. Somebody else. Who else? Okay, yeah, on the aisle. What year? 75. And the month? February what? 11. Was that a Tuesday? Terrific. Somebody else? Yes, sir. What year? 95, did you say? And what month? November. November what? 4th. Was that a Saturday? Yes. Somebody else? What's that? Little boy there? All right. Well, if he's shy, you can say it for him. What year? 2003. And what month? May what? 21st. Was that a Wednesday? 31st. Was that a Saturday?
Yep.
Excellent. Thank you very much. Your mom was there. She knows. I'll tell you what. Anybody here who perhaps does not know the day of the week they were born but would like to find out? You would? Okay. Now, of course, if you don't know what the birthday is, I could just make up an answer, and you'd probably believe me, but I don't want you to have to do that, so I brought something with me. You know, there's an app for everything these days. I'll ask you to help me out here. So all you have to do is type in the year. when he gives it. So what year were you born?
2003.
So 2003, so type in 2003, and what month?
March.
March what?
March
31st. Oh, wasn't there another one up there? So I think that was a Monday. Can we confirm it was a Monday? It is a Monday. I'll tell you what, as long as you have the app, that calculator will go as far into the future as the year 3000. It'll go as far into the past as 1600. It'll go below that, but then we get off the Gregorian calendar, and that trips me up a little bit. So you give me a year, any year you'd like, between 1600 and 3000. Make it interesting.
1883.
1883, okay. And what month would you like?
October.
October what?
October 7th.
October 7th. Was that a Sunday? Yes, and it was cloudy, I think. Thank you very much. Thank you. In fact, anybody else who wants to find out their birthday, see me after the show. I'll be hanging out at that table, and I'll be more than happy to tell you. Now, folks, if I were performing for a different kind of audience, say at the Magic Castle in Hollywood or even the Magic Circle in London, I might follow this up with other feats of magic and mind. But for an audience such as this one, I actually prefer to break the magician's rule and explain to you most of what you've seen me do up here and more. In fact, I'd like to conduct the rest of this program, the next 30-40 minutes, very informally. So feel free at any time to interrupt me with questions, even if it has nothing to do with what I'm talking about. Now, Matt, I'd like to take advantage of having you here in the audience. Why don't you get us started asking we have not set up anything in advance. Why don't you take the first few questions, and then I'll let the audience at me as well, see what they'd like to.
Before we commence with the questions, can we have a big round of applause for everything asked? It's genuinely daunting watching. Actually, the question I had, because doing similar work but much lazier, is I know that for all the stuff I do, I pick a trick I want to learn, and then I hone learning that trick. So I look up the methods and the tricks you can do, and then I gradually learn the steps and I practice, and my girlfriend gets very annoyed with this, and gradually I'll hone it. So to what extent do you go, you know what, I want to learn how to do this calculation,
Yeah.
and to what extent do you discover you can do something and then use it on stage?
So, so is your question how, for example, did I come up with my method of squaring numbers, or how would I go about practicing it, or?
Do you decide, do you have to learn it, or is it an innate ability?
So, yeah, okay, so I would say everything you see me do up here is a skill. Something that I sat down and practiced with. None of the numbers, it wasn't like I woke up one day and, you know, saw my alarm clock and squared the number and said, wow, what just happened? So no, for me, I've always loved numbers. I've always loved maths. And in fact, the maths in some ways came before the magic. It wasn't like I mean, I've had independent interests in both, performing and in maths, but a lot of the math skill had come about before I started performing it. I was performing magic, traditional magic shows for children, for instance, long before I started doing what you're seeing up here. So I'll tell you though how let me show you the method that I use for squaring numbers. So if anyone in the audience wants to start honing their skill on, and that's one thing you should all leave today, is how to square numbers pretty quickly. So give us a small two-digit number as our first example. What was that?
42.
42, a nice number for many. 42. Now to square 42, we go. I'll start by looking for the nearest easy number. So what's the nearest easy number to 42? 40. So I go down 2 to 40. Now whatever comes up must come down. If I go down 2 to 40, I then go up the same distance to the number 44. So the first part of my calculation is I do 40 times 44. Now if there's only one thing you remember about all my methods tonight, it should be this. I do all of my calculating from left to right. That's the opposite of how you might do it on paper. On paper, many people go from right to left, right? The ones, the tens, the hundreds, the thousands, and so on. But that's backwards. We read numbers left to right. We pronounce them left to right. You should calculate them left to right, at least when you're doing it mentally. On paper, you could go either way, but mentally, we think about our numbers from left to right. So let's start with 40 times 44. I'll ignore the 0 for now. I like 0, so I'll ignore that. And do 4 times 44. Now, everyone together. 4 times 40 is what? 160. Okay? Here, I'll write this down for now. 160. 4 times 4 is 16. Add those numbers from left to right, and we get 176. So 40 times 44 is 1,760. Almost done. All we have to add to that is the square of the number that we went up and down. We went up and down 2. 2 squared is 4, and there's your answer, 1,764. Yeah. Here, let's try another one. Let's do a couple more examples. I want to make sure everybody gets this really well. How about another 2-digit number, sir?
27.
27. Okay, so this time with 27, I like that because now the nearest number is above. So we'll go up 3 to 30. Therefore, we go down to what number? If I go up 3 to 30, I have to go down 3 to 24. Okay, next we'll do 3 times 24. 3 times 20 is 60. 3 times 4 is 12. Mentally add 60 plus 12 from left to right, and you get 72. With the friendly 0, that's 720. You could actually start to say your answer because the answer is what? 720 plus the square of 3, which is 9, 729. Okay. Now, why does this work? I'm here with a math and computer science audience, so let me write one piece of algebra for the whole night. If you're squaring a number, a squared, you can write that as a plus d times a minus d plus d squared, where d is your distance to the nearest easy number. Does that check out? Those that remember their algebra, a plus d times a minus d, if you multiply them, you get a squared minus d squared. When you add the d squared, the d's go away, and you're left with a squared. So for instance, for 27 squared, d is 3. That's my distance. So I do 27 plus 3 times 27 minus 3 plus 3 squared. That's the calculation we did. Now, I don't think about the algebra as I do the calculation, but the algebra gives me confidence that this method's always going to work. Okay? And then once you get good at squaring 2-digit numbers, once you've honed that to a degree where the 2-digit numbers just take you a second or two, or in my case, confession time, I've been squaring 2-digit numbers now for more than half my life. The 2-digit numbers have become memorized. Not intentionally. I didn't sit down to memorize them. I just know them. Just like many of you might know 13 squared is 169. They might not have forced you to learn that in school, but some of you just know it because you've seen it often enough. But if you want to square a 3-digit number, like let's say the 3-digit number was 227. Then this time, I'll go up or down to the nearest 100. I'll go down 27 to 200, up 27 to what? 254. Now we do 200 times 254. What do you get if you double 254? Double 250 and that's 500. So double 4, you get 8. So 2 times 254 is 508. See, working left to right. So 508 with 2 zeros is 50,800. What do we add to that? The square of 27, which is staring you in the face, right? 729. And now this is what I'm doing. That's why I'm starting to say, I can say 51,000 while I'm adding the 800 to the 729 to get the rest of the answer, 529. Okay? Let's hear it for algebra. Yeah? What else would you like to know?
So when you were squaring 7,721?
2-1 was that? Yeah, okay.
Was that a normal length of time, or was
No,
that?
that was much hard. That was much slower than usual, and the 7-7 actually probably tripped me up a little bit. Thanks a lot. But I'll show you what I did, or what I should have done, anyway.
I was watching, thinking, is this just theatric, or was it?
You know,
slightly more
it would be,
complicated?
the audience likes it more theatrically when I make mistakes and recover. But I make enough mistakes naturally that I don't dare plant them in intentionally.
I have that skill too.
But if you'd like, I can go through the steps of that one. And so the number was 7721. Okay, so here are the steps. And I'll show you something freaky that happens in the middle of it. For those of you that like words more than numbers, let me show you what happens in the middle. So 7721, now the nearest easy number would be what? 8,000, right? I like all zeros if I can. So I go to 8,000. Now how do I figure out the number to go down to? I could say, well, this is 279 away and do that subtraction, but that's kind of yucky. I don't want to do that subtraction. I hate subtraction if I can avoid it. So instead, what I do is I take this number, actually just the last 3 digits of this number, and I double it. Okay, if I double 7721, you'd get, if I doubled 7721, I'd get 15,442. And that tells me that this other number is 7442. Why? Because these numbers are the same distance from this number. So if you add this number and this number together, you'd get twice the middle number. So that's how I figure out this number. I double this number. Actually, I just double 721 to get 1442, and that tells me that it's 7442. So I find it sort of in an indirect way. Then I take 8 times 7442. And the first mistake I had made up on stage was I did 7542. First I had 7442, then I had 7542. That's when I said 60,000, but then I knew it was close, and anyway, so yeah, it was 59,000. Anyway, so I do 7442 times 8, and I break that up into 2 parts. I do the 8 times 74, which is 592, 59,200. Then I do 8 times 42, which is 336, to get 59,536. At that point, I say the 59 million. Get that out of my memory and into yours. And then I hold on to the 536 with a word. And in this case, the word was Elmish. And I'll tell you where that word comes from later. Let me not go into that quite now. But anyway, now I square 279. How do I do that? I won't write it down. 300 times 258 plus 21 squared, 77,400 plus 441 is 77,841. 841, I'll put the 8 on my fingers, okay? That's what I should have done anyway. 8 on my fingers so I don't forget the 841. Or I could turn 841 into a word like fort or fruit or fart, and I'll tell you where those come from later. You don't get to hear fart in the math talk nearly often enough, Matt.
And wouldn't you tell you where it's going to come from?
You know, exactly. So anyway, so here we go. So I now do 70, what do I have? I got 59,000, I've said the 59 million, I'm holding on to Elmish. I do 279 squared, that's 77 fart. I got the 77, add that to Elmish. 77 added to 536 gives me the 613,000, finally with the fort or fart, 841. That's how the calculation's supposed to go. Thank you.
Have you named all the 3-digit numbers?
I have not. So here's what I do. Here is what I'm using. It is a phonetic code that was actually developed in the 1800s. It's called the Major System. And it's well known to magicians and cognitive psychologists, where every digit gets a consonant sound. So let me quickly write on the board here. So I only have consonants for each of the digits. Okay, so for instance, the 1 is the T or D sound, the T t or d sound. The N, the 2 is the N sound. The 3 is the M sound, and so on. And some of you are thinking, well, how do you memorize that, right? Well, there are even mnemonics, memory tricks for learning this list. For instance, a typewritten T has 1 downstroke. When you draw a T, your hand goes down once, and if you can remember the T sound, you can remember the phonetically similar D sound. The N has 2 downstrokes. The M has 3 downstrokes, and so on. Here, oh, or if you turn a 3 on its side, it looks like an M. The 4 ends in the letter R is how to remember that 4 is R. 5 is an L. If you put a 5 on your fingers and you look between your index finger and your thumb, you will see an L. It's cheap, but you'll remember it, and that's all that matters, right? The 6 is the hardest one. It's one of the sneezing sounds, the ch, sh, or j sound. A backwards J kind of looks like a 6, or maybe that 6 looks like a nose that's about to sneeze. I don't know, something like that. Anyway, next we have a 7 is a K or G. That's the k or g sound. That's a hard G like goat, not a soft G like giraffe. Giraffe has a J sound, which we've already used. Spelling does not matter here. It's all phonetics. You can draw a K with 2 7s like that, sort of a special K. Next we have, as an 8, is the F or V, the fa or va sound. A cursive F kind of looks like a V, or like an 8, or a skater does a figure 8. You can see that. How about you tell me? 9 is P or B. How would you remember that? Yeah, just backwards or upside down 9. How about 0 being S or Z? What would you do to remember that? 0, right, begins with Z. It's one of the hissing sounds. Now, once you have this code memorized, and it only takes like 10 minutes to know this list backwards and forwards, you can now take numbers, even meaningless random numbers, and turn them into words by sticking vowel sounds wherever you'd like. So for instance, a number like 59 would have what? I'd have an L for 5. The 9 would be P or B. What words could you create? You could get words like loop, or lip, or lab, okay? Or any of those would be fine. How about 536? Now, I didn't need a mnemonic for 59 because I already said the 59 million out of my system. But I had to hold on to the 536, and this is where I got into trouble. I had an L, I had the M, and I had the SH sound. And the best I could come up with was Elmish, which is not even a word maybe outside of Lord of the Rings, you know. But I mean, there probably is something out there, but I didn't see it, and I still don't. Now, there are actually dictionaries. You go online, phonetic code dictionaries. Like if this was part of a credit card number and I wanted to remember it, I'd look that up first after trying. But anyway, Elmish was enough to stand out like a sore thumb. I wasn't gonna lose that. And then I squared the 279, and when I squared 279 and got 77,841, now you see I was going to add the 77 to Elmish to 536, but I had to hold on to the 841 so I wouldn't forget that. And what are the sounds for 841? The sounds of 841? F, R, T. How do you not think about the word fruit? Yeah, you see my problem. So that's how the numbers intersect with what I'm doing. You know, if you have the time to sit down and memorize long strings of numbers, I've used this to memorize my passport number, all my credit card numbers. I mean, phone numbers we don't need anymore. We pick up the phone, we hit, you know, our contact or speed dial. But for things like credit card numbers that you give all the time, or filling out passport numbers or something, very much comes in handy a lot. Or if you want to show off and someone says, well, you know, how many digits of pi do you know? Well, you say, well, you know, approximately this. I know. How are you going to check this? I'm running out of ink. Anyway, here are the first 60 digits of pi. Thank you very much. And now, but you're thinking, but okay, so how do you check this? Or how would you memorize this, right? So here are the first 24 digits of pi. So the first 5 digits, 31415. Okay, now the cheat sheet is not on the board. What's 3? M. And 1? T or D. 4? R. 1? Good, I heard more people on that second one, okay. T, and what about 5? L, great. So the first 5 digits of pi become my turtle. My turtle. And my turtle can only go back to 31415, okay? You put time into looking for word patterns in there, and the first 24 digits become my turtle Pancho will, my love, pick up my new mover Ginger. My turtle Pancho will, my love, pick up my new mover Ginger. Say that sentence 5 times and you'll unfortunately have it memorized. And with that sentence, you'd have the first 24 digits of pi. The next 17 digits that starts off 338 or MMV becomes my movie monkey plays in a favorite bucket. But I like these next 19 the most. They say, ship my puppy Michael to Sullivan's back rubber. If you wanted 100 digits of pi, I won't give you the next 40 digits, but I'll tell you their sentences. They are a really open music video, cheers, Jenny F. Jones, followed by have a baby fish knife so Marvin will marinate the goose chick. Thank you very much.
I do like it when how many digits of pi do you know is, well, depends how much ink is in the pen.
There we go, yeah.
So I obviously have a monkey bucket worth of questions that I could ask, but if anyone has a question from the audience, we will throw it open.
Yeah,
So
what else?
a gentle hand up, as this guy is modeling now, will be perfect. Yes.
What can't you compute?
What can't you compute?
What can I not compute? Oh, gee. Well, I have to say, I'm very much a base 10 baby. Okay, so don't ask me to do things in binary or hexadecimal. And I like integers, whole numbers. I mean, if you give me a decimal problem or an irrational problem, I will do an approximation as, to a few digits. The largest problem I've ever done is in front of an audience, though I rarely do it, would be multiplying 2 different 6-digit numbers. Not squaring, but 2 different 6-digit numbers. I will do a pair of 5-digit numbers, or at least square a 5-digit number for you tonight. But the 6 digits is just too much. It takes too long. The probability of mistake is too high. So that's about as far as. And by the way, I would have trouble, let me tell you this, I would have trouble adding 2 6-digit numbers, for that matter. If you rattled off 2 6-digit numbers very quickly, I don't know that I could repeat the numbers back to you, the problem back to you, much less the answer. So I run out of memory, short-term memory capacity at about 10, 11 digits. What I use to give myself additional memory is the phonetic code. But if I don't have time to do, if you just rattled off a 6-digit number and a 6-digit number, and I don't even have time to make phonetics out of them, I don't think I could repeat them back to you.
Do you do much of the outsourcing things to physical positions?
Only if I can hold 2 digits on my 2 hands. So on the first hand, I can hold 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that's sign language. And on the other hand, I could do the same. So if I'm playing backgammon, which by the way is my favorite game, anyone wants to play afterwards, see me. If I'm playing backgammon and I have to count the race, and I have to say how many checkers is it, how many pips does it take before I get off the board, and I see it's going to take me 84 pips. Then on one hand I'll hold the 8, on the other hand I'll hold the 4, and then I'll count my opponent's position, and I don't worry about forgetting my pip count because I'm literally holding on to it. So I do that, but I don't do anything more. I don't do any kind of loci or anything.
He's not dancing. These are genuine moves, remembering.
That's right. No, that's right. No, this is just my own natural hyperactivity coming out.
Okay, any questions from the crowd? I'm going to go with N guy, then we'll come back to you, miss. Yep.
At what age did you start practicing these exercises?
At what age did I start practicing these exercises? you know, even from an early age, I mean, so what did I do? I mean, I would say around kindergarten, first grade, I learned my multiplication facts up to 10, nothing special. I learned it from a game where you got rewarded by knowing the answers to the addition, subtraction, multiplication questions. So I wanted to get good at the game. I liked taking problems and pulling them apart and doing them in more than one way. So like if I'm going to multiply 42 times something, I might multiply it by 6, then 7. Whatever number I had, I'd do 6, then 7. Or I might do it the other way, multiply by 7, then 6. Or maybe I'll multiply by 40, then multiply by 2 and add them together. So I like the fact, and I still do, love the fact that you could take a math problem, do it lots and lots of different ways, and if you're careful, you'd always get the same answer. Now, how I came about the squaring of numbers was actually, I was learning algebra at the time, but I didn't know how to use it to develop this. Here's how, I remember the day I was in 8th grade, or as they say out here, year 9, taking a bus down to the downtown Cleveland, Ohio, where my father worked. And like many 13-year-old, I was thinking about the numbers that added up to 20. And I wondered, how large could the product of two numbers that add up to 20 become? And I thought, well, 10 and 10 in the middle, I thought that, you know, multiply those, you get 100. I didn't think you could get any higher than 100. And I tried a few other examples. Well, 9 times 11 is 99, which was almost 100, but it was shy by 1. 8 times 12 is 96, almost 100, but shy by 4. 7 times 13 was 91, almost 100, but shy by 9. 6 times 14 was 84, still is. 5 times 15 is 75. And I noticed two things. I noticed that, hey, as you pull these numbers farther apart, the product is getting smaller. And how far away were they from 100? 1, 4, 9, 16, 25, the squares. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. I said, that's really cool. I wonder if that always works. So how do you tell if something always works, at least when you're 13? Try another example, right? And if it doesn't work, then it was just a coincidence. But so I said, all right, what if the numbers added up to 26? You know, so I started in the middle with 13 and 13. Multiply them together, that gives a 169. 12 times 14 was 168. 11 times 15, 165. 10 times 16 is 160. And again, the numbers were getting smaller. And by how far were they from 169? 1, 4, 9, 16, 25, 36. I said, wow, that's really, really cool. And then I had what may have been the most creative mathematical idea I've ever had in my life, which stinks because it was over 30 years ago. But I said, you know, you could apply this pattern as a way of squaring numbers. Let's say you wanted to do 13 times 13. Instead of doing it the usual way, make it easier on yourself and do 10 times 16. Because that's an easier problem. That's 160. Then all you'd have to add would be 1, 2, 3 squared. Now, when I showed my algebra teacher this, it actually showed up in class one day. She left an answer on the board as 108 squared. And I blurted out, that's 11,664. She said, why, yes, it is. How did you do it? I said, I went down 8 to 100, up 8 to 116, multiplied them together. 11,600 plus the square of 8 is 64, 11,664. And now she actually knew her algebra well enough to realize what was going on. And she said, that's very good. Can you prove that? And I said, oh yeah, you want proof? I'll give you proof. And I showed up pages and pages of examples. It works for big numbers, small numbers, negative numbers, fractions. It works all the time. So anyway, I became an applied mathematician, I think, as a result of that. Anyway, but that's a long story short. So that's how the thoughts of Benjamin's theorem came at a very early age.
So the moral is, if you want your kids to be good at maths, make sure they have a very long bus trip to school.
There you go.
Miss over here, yes?
Yeah, how many steps in the algorithm for the birthday? How much more complicated is it when you go to centuries in the future or past?
Oh, so the steps in broad strokes, I'm not going to go to, because we're getting towards the end of our hour, I'm not going to go through all the details, but in broad strokes, to calculate the days of the week of the birthday, you use the year, the month, and the date. And you have a number for each of those. You add them together, divide by 7, and the remainder tells you the day of the week. Okay, so for example, somebody give me their birth date, and I'll do it out loud for you, even though you don't have all the details ready. So okay, so what is your birth date? And I always ask for the year because that's actually the hardest part of my calculation. So I want to do that with an open mind. What year? 1991. Okay, so now so anyway, so every year gets a code number, and 1991, the code number is 0. Okay, then I say what month? August. Okay, so August, that gets a code number of 1. August what? 27. We add 27 to that. 0 plus 1 plus 27 is 28. When I subtract off the biggest multiple of 7, that would be 28. We get 0. And day 0, none day, is Sunday. And you were born on a Sunday. Okay. Now you do. Now you know. Okay, so that's now, and so as far as how it affects other centuries, hardly at all. So the from the 2000s, 1900 is just 1 day forward of the 2000s, and 1800 is 3 days forward, and 1700 is 5 days forwards. And guess what? 1600 is the same as the 2000s. The calendars go in a 400-year cycle. So once you know,
That should be a Tuesday.
Is that correct, or is it Tuesday?
Actually, let me say, and I may have made a mistake only because I use a different code when I'm up on stage than the one that I teach, because it's
Well, this talk is over.
That's right. No. It's because the one I learned, you know, in high school, like many years ago. I'm gonna try this one. 113. So okay. So with 1991, I'm gonna do that. 1991. Maybe that year code should have been 1. Oh no. It is. Oh, is it 2? Yeah. Okay. All right. I know the reason, as I said, I do this I wanted to do this in the way that you would do it on paper, with the way that is taught in my course. But you're actually right. 2 plus 1 plus the year code for 1991 should have been 2, and that gives me 30. Minus 28 is 2, and you know what day number 2 is? Tuesday, right? Of course. So that should be Tuesday, and so that's correct. But anyway, that's the essence of it. But if, by the way, and this is a horrible time to make a sales pitch after I've just made a mistake, but I'm going to say it anyway. If you're interested in learning more about any of the processes that I do, whether it be how to do math in your head, addition, subtraction, multiplication, division, percentages, decimals, fractions, everything I know about mental math is given in this 12-lecture DVD course called The Secrets of Mental Math. It is everything I know, including how to calculate the birthdays, memorizing numbers, estimation, everything, that cube roots and so on. And they sell this in the United States for $200.
The trick of the magic numbers that you did.
What was that again?
The number that
The magic square.
Magic squares.
The magic squares is not in this course, but it's in another one of mine. But let me say this one. This one sells in the United States for $200. I sell it here for $30. 30 pounds. 30 pounds. So if you're interested in that,
What age group is that for?
if you know your multiplication tables through 10, then you can understand almost everything in this course. Okay, I won't ask. Also, I have another course. While this is about math in your head, this is math in your school. It's called The Joy of Mathematics. It's 24 lectures, middle school and high school level mathematics, everything from algebra to calculus, with emphasis on the fun topics, pi, e, Fibonacci numbers, magic squares, mathematical games, mathematical magic, as well as algebra, geometry, trigonometry, calculus, probability, with an emphasis on what I thought were the most fun and important parts of those subjects. It's twice as many lectures as this course, and so even though this is 30 pounds, I sell this for 40 pounds. Finally, I have have a course on discrete mathematics. That is secretive mathematics. It's the math that underlies computer science and cryptography. It is, for those in the know, combinatorics, number theory, and graph theory. It's also 24 lectures. It's also 40 pounds. So I have easy, medium, and hard for 30, 40, and 40. Or you can get all three for 200 pounds. And if that sounds like a bargain, then you really need this course. Actually, if you get all three, it's 100 pounds, and I'll be up here if you're interested in. Anyway, so that's the end of the sales pitch there.
So the first one's
the mental math is
a lecture, and the other one's under 2 somewhere. So one more question, and then very concise, and then we're going to go. I'm going to go with a very patient guy at the front, if that's okay. Yep.
Briefly, how do you do the missing digit?
How do I do the missing digit?
Can I interest you in the greatest?
It's actually in, no, I will explain this to you. I'll explain this one to you. But it's in the Joy of Mathematics in lecture number 9. Good, all right? Because it's all based, lecture 9 is called The Joy of 9. And when I was a kid, my favorite number was 9. I even said I liked Sarah's birthday because it had 9 and a 9 and an 18 in it, right? I said, oh, these are great numbers. And what's so special about the number? What's so special about the number 9? If I write down all the multiples of 9 that I can on this board, then what do they have in common? They add up to 9, right? The digits add up to 9. 1 plus 8 is 9. 2 plus 7 is 9. 3 plus 6 is 9. Wait, there's an exception up there. Do you see it? Yeah, 99. But that adds up to 18, which is a multiple of 9. So here's the deal. Probably taught to you back in primary school, though probably not proved to you. But a number is a multiple of 9 if and only if, when you add the digits, you either get 9 or 18 or 27 or 36, 45. They have to add up to a multiple of 9. Now, the numbers that I had to work with were really rather nice. They came as squares of 2-digit numbers that came from the audience. And if any of the numbers that were called out were multiples of 3, usually a third of them are, then their square will be a multiple of 9. So look at 5625. What do those digits add up to? 5, 6, 2, 5 adds up to 18. So is that a multiple of 9? Yes. 7396, that adds up to 25. Is that a multiple of 9? No. 4225, that adds up to 13. Is that a multiple of 9? No. 6084 adds up to 18, so that actually is a good one. And the number I used, I just said casually, let's take the last number on the board, 1764. I didn't take it because it was the last. I chose it because it was a multiple of 9. Now, how did that help me? So if you take 1764, if you've got a calculator, you multiply it by a 3-digit number, say, you'll get a 6-digit or 7-digit answer. Okay, Sarah, I see you're doing one. So how about you have how many digits in your answer, 6 or 7? 7. Okay, so quickly call out 6 of your 7 digits.
1, 0, 2, 0, 6.
You got one more, right? Because you had a 7-digit.
0.
0. Okay,
No,
so
no, 2. Yeah.
Okay, so you've called out 102062. Okay, now I don't know what Sarah's 7-digit number is. I still don't know it. But you don't. Well, do you know her actual 7-digit number or just the missing one? Oh, you're just messing with me. Okay, I've had that happen to me in shows. But anyway, so I don't know what her 7-digit number is, but I do know this. Her 7-digit number has to be a multiple of 9, right? Because she started with a multiple of 9 and she multiplied it by something. So the answer still has to be a multiple of 9. So what am I doing as she's calling out these 6 numbers? Adding them up. 1 plus 2 plus 6 plus 2 is 11. So what number did she have to leave out to reach a multiple of 9? 7. Did you leave out a 7? Good thing. Now there's a question that's begging to be asked, right? What would happen, suppose she called out her numbers, suppose she called out her 6 numbers, and they, like let's say this was actually a 0. She said 102060. Then those numbers would add up to 9. So what did she leave out then? You don't know. It could either be a 0 or it could either be a 9. What do you do in that situation? You guess. But as a magician, you can do it in such a way that it does not look like guessing. And you saw me do that on stage. There were 2 people that I said I was having some trouble with. I saved them for the end, right? I said, concentrate on that. I said, I'm getting a lot of nothing. Which of you left out a 0? One did. I said, aha. The other one, you didn't leave out a 0? Just thinking of nothing. Okay, I'm getting it now. You left out the number 9. And it looks like you got it right the first time. Yeah? Yeah. Thank you. I hope you still respect me. So anyway, so that's... Now, of course, my favorite number... I mean, as a kid, I liked 9. As I grew up, I got into more, irrational numbers, transcendental numbers. My favorite number, of course, was pi. And is it still, which, now, just to show you how clueless I am, I don't even remember which board I wrote it on. Was it on
that one?
This one? Thank you. So before I go into my grand finale, I want to share with you a song about my favorite number that I wrote a few years ago for Pi Day. It's coming up, March the 14th. And I think goes over better in the States, right? 3:14. But anyway, let me share it with you to convince you, if nothing else, that there's no connection between talented math numbers that did more. But then my teacher said, I dare ya to try to find the circle's area. Despite my every action, I couldn't find a fraction. I can't remember if I cried the more I tried or circumscribed, but something touched me deep inside the day I learned of pi. Oh, pi, pi, mathematical pi. Twice 11 over 7 is a mighty fine try. A good old fraction you may hope to supply, but the decimal expansion won't die. Decimal expansion won't die. Pi, pi, mathematical pi. 3.1415926535889. A good old fraction you may hope to define, but the decimal expansion won't die. Thank you. Is this thing on? All right. Okay, last thing, then I'll let you go, because somebody earlier asked about squaring larger numbers, 5 digits and so on. So let me do that for you, and then I will let you all go. How about let's create a 5-digit number. How about the row I haven't used yet? How about let's go up this aisle. If I can get 5 of you, each call out a single digit from 0 to 9. That will be my 5-digit number. 7, 6, 4, 3, 5. 76,435 squared. Let me explain to you how I'm going to attempt this problem. We'll break the problem down into 3 parts. I'll do 76,000 squared plus 435 squared plus 76,000 times 435 times 2. Add all those numbers together and, with any luck, arrive at the answer. Now let me recap. Thank you. While I explain something else. As I do this last calculation, you will hear certain words as opposed to numbers creep into the calculation. You now know what that is. I'm using the phonetic code we saw earlier. I don't want you to think you're seeing something out of Rain Man here. There's definitely a method to my madness. Definitely, definitely. Okay. One last suggestion for those who in the audience has a calculator's checked it out. Probably a few of you should have a 10-digit number beginning with 5, ending with 5. In between, I don't know yet. There's at least a 50% chance that I'll make a mistake somewhere in between. If I do, don't tell me what the mistake is. Just say you're close or something, and I'll try and figure it out, which can be pretty entertaining in itself. If, however, I am right, whatever you do, don't keep it to yourselves. Make sure everybody knows that I got the answer right, because this is my big finish, okay? So without any more stalling, here we Go. I'll start the problem in the middle with 76 times 435 times 2. 435 times 2 is 870. 76 times 87 is 6,090 plus 522 is 6,612. 6,600, I think that's right, 6,612. That becomes 66,120. 66,120 becomes Judge Tennis. Judge Tennis is 66,120. Judge Tennis. Okay, next I do 76 squared, which is 5776, so I can say 5 billion. Take the 776, add that to Judge. 776 plus 66 is 842 million. Tennis, tennis. Okay, finally we do 435 squared. That's 400 times 470 plus 35 squared. It's 188,000 plus 1,225. It's 189,225. No nail if I need it. No nail. Take the 189, add that to tennis to get 309,225. Good. Thank you all very much. I hope you enjoyed Mathemagics. I'm Arthur Benjamin. Thank you.